Okay, so let's do a few exponential growth problems. These are exceedingly applicable. Uh, I have three different models up there. You could really use any of these, but I think I'll start with the one on the left. Suppose you have an exponential growth function with f of 2 equal to 5 and f of 6 equal to 11. So just so we can see if we're winning, I'll go over to Desmoth and say, hey, input 2 ought to come out at 5. Input 6 ought to come out at 11. If I don't go through those two dots, it's not the right function. And you know the basic shape of an exponential function. So what I do, particularly if I'm using that one to the left, I'd put in, hey, 11's my output. Oops, I'm doing the one on the right. 11 is my output when 6 is my input. 5 is my output when 2 is my input. And the truth is, I usually like having the bigger one on top because the secret technique here works really great is dividing the left sides and dividing the right side. If they're really equal, then you can divide. And 11/5 is exactly equal to CB to the 6 divided by CB squared, right? And so it's fairly nice to have the bigger power on top. Notice how nicely the right-hand side cancels. So I have 11/5 equals, the c's cancel, and I just have b to the 4th. Okay, well, then it's pretty easy to solve for b. b is 11/5 to the 1/4. Okay, well, that might not be your favorite number in the world, but it's nice to have b. And once you have b, it's pretty easy to get c from one of these equations. I'll pick this one here. Seems easy enough. Let's see. So this is, instead of b squared, how do you square to the 1/4 power? Well, 1/4 squared is to the 1/2 power. So I have 11/5 to the 1/2 power. Okay. And then, well, how do you get c by itself? You actually have to take this equation and you have to multiply both sides. Well, technically, you could divide by 11/5 to the 1/2. But dividing by a fraction to a fractional power is a little messy. And generally, what makes better sense to do is put a minus power. Notice you add these exponents and they cancel over there. You would get the same thing if you divided, right? Because a negative is really having it in the denominator. These two cancel, and so c is equal to that fairly nasty thing there. Well, so what's the punchline? The punchline is if you know c and you know b, you know what the function f of x is. Okay, so f of x equals your mess for c times your 11/5 to the 1/4 raised to the x. Now, instead of writing x to the 1/4 and then writing raised to the x, I'm going to write to the x/4, right? Because the powers multiply. Okay, and that's the function that goes through those. Let's just go to Desmos, make sure we're not telling ourselves vicious lies. Let's see, what did we have? We had 5 times 11/5 raised to the negative 1/2 times 11/5 raised to the x over 4. Yay, it goes through our dots. Now, you might say, God, that looks like the most ugly thing in the world. And remember, it might not be, that's making it really precise. But if I got C and B as decimal approximations, that might sort of make you feel a little more comfortable. Probably not quite as good a quality answer, but if you wrote this as 3.37 times 1.218 to the x, that sort of looks a little more familiar, and you can see that it's an exponential graph there. Basically the same one with a little rounding error. Okay, so those were abstract points, but there's all sorts of biological and financial applications that do the same thing. Here's one: a clump of 3,000 bacteria grows to 6,014 hours. How many bacteria should we expect in 24 hours? So you can sort of see really what I have, if I'm using that same model, is 3,000 comes out. No, I'm getting a smaller font there. Let's try and get the same font. 3,000 comes out at time 0. Well, that's a pretty good equation there because, right, b to the 0 is 1. So I actually know that c is 3,000. It's really nice when you get that initial value. You can basically just plug it in. And 6,000, no, I want the same font. 6,000, now instead of writing cb to the 14, I'm just going to say I know what c is, times b to the 14, and now I can pretty much solve for b, right? Let's see what that is. That's going to be, I'm going to have to divide both sides by 3,000. 6,000 divided by 3,000 is 2, equals b to the 14. We'll just take the 14th root. Can you believe that we're just saying just take the 14th root? But, you know, hey, that's the breaks. Okay, so b is the 1/14th. So what's your model there is, your model is f of x equals 3,000 times b, 2 to the 1/14th, but then that's to the x, so you can write 2 to the x 14th. Now, notice that that looks very much like this model on the right. That's the half-life model. It's c times 2 to the t over d. And in fact, that model, if you're either have the not half-life, doubling time, it would be exactly that model with a minus sign if it was the half-life. But you could actually do this problem really perhaps more simply, not really perhaps, definitely more simply. If you used that equation, you'd say, hey, what's my initial value? My initial value is 3,000. Hey, what's my half-life? My doubling time? My doubling time is, can you see, it goes from 3,000 to 6,000 in 14 hours. So if you know what you're looking for, you can save all of that work and you can get to the model right there. And you can say, boom, didn't have to do that, okay? That's the benefit of having 3 different models. You might say, why do we have 3 different models? Different models work better in different situations. So either way, you get that. And the question is really asking how many bacteria should be expected in 24 hours. So what do? We take this model and we say y equals 3,000 times 2 to the 24 divided by 14. Then we go over to our friend or any convenient graphing calculator really, and we say 3,000 times 2 to the 24 divided by 14. And I just have to mention, like, if we were our parents, you wouldn't just have something you could punch in effortlessly 2 to the 24/14 and it spits that out. Okay, so it's approximately 9,844. So the bottom line is, be glad you're doing math in this era. 9844, was that what we had there? 9844. That's a wrap. Hope that's helpful.